Hi Calc. I want to go over this concept briefly. We're working on limits, and if you're a mathematician, this is a really important concept. I don't test on this, but this is the foundation behind the idea of a limit, okay? So the idea behind a limit, how it is defined, the definition: it's a function defined on an open interval containing C, and let L be a real number. So this statement here is that the limit as x goes to C of this function equals to L means that for each epsilon greater than 0, there exists a delta greater than 0, such that if x minus C is in between 0 and delta, then f of x minus L is less than epsilon. Okay, so again, I'm not going to test you on this, but the idea is, if I just sort of break it down, what it means is, this is the limit right here. So it says, what it says is this: if I can get the output within plus or minus epsilon, then the limit exists. So how wide do I have to make plus or minus delta so that if this is true, then I can hit the target in here? So if x is in between these values, then y must therefore be in between these values, okay? So if x is in between these values, this guarantees that the limit will fall in between plus or minus delta. And if I can say that I can catch the limit within this box, then it exists. Then it exists. So if you remember those three cases we talked about before, like if something's unbounded like this, I can't catch it because it's going to shoot right out of the box. So that's why this doesn't have a limit. Plus or minus epsilon's a really tiny box. So see, these are too far apart. Plus or minus epsilon means that they have to be approaching within a very tiny window. And these are not approaching each other within a very tiny window. They're outside of plus or minus epsilon. So that's why the limit fails. And here, like I said before, since it increases oscillation, it sort of jumps in and out of my target box, and I can't catch it. And that's why the limit doesn't exist here. So for us to say that the limit exists, it's like it has to fall like within a particular box or target, and then we can say we've caught it, it's in here, right? And then we can say the limit exists. Okay, I know this is really technical. If you're a mathematician, please review this, look over this. I would suggest even read over this. I won't go over this in the lecture, but I would say, like, if you're a math major, why don't you look over this example and think about what they're asking. Now, in terms of class, I am going to ask stuff like this. These are analyzing a graph to find the limit. Now, if you notice in this example, there are actually functions, and I most likely, let me phrase that better. I do not usually give the functions when I give graphs. So let me just look at your book real quick. Yeah, so like on a exam, it's not uncommon for me just to give a scenario like this, okay? Where there's no distinct function, there's just like pictures, and then you have to find the limit of the pictures, okay, of the function. This is actually one function, it's complicated, but it's one guy. So I'm saying that because I don't want you to pay too much attention to the function. I want you to actually look at the graph. Now, this does not exactly match your homework. Your homework, the book, the edition that you're on now looks like this. I'm looking at what you guys have as a PDF. Okay, and you can even slow down the video and just write down what your homework's going to be because I'm scanning it as we talk. Okay, so, but this is incredibly similar to what your homework is going to look like. So let's try some of these. Now, remember, some of the limits will fail, right? Use a graph to find the limit if it exists. So remember, I gave you the three cases where it fails to exist. Do you remember what they are? Unbounded, gap, increasing oscillations, right? That's where they fail to exist. All other cases exist. And let's say why if it fails to exist. Okay, so here we go. This is the idea. We want to take the limit as x goes to 3 of this function. So what x goes to 3 means is that you're approaching x from both the left and the right side. And as you approach x goes to 3 from the left and the right side, you want to know what the height does. So on the right side of the function, I'm approaching this height. And on the left side of the function, I'm approaching this height. So we would say from the left and from the right, we're approaching the same height. Now, if this is looking insanely easy to you, you're getting it because it's actually this easy. It's actually this easy. You're just trying to figure out what is the height as x goes to 3. And as we can see that the height is a 1. Now, what gets students stuck is that you have to remember it's an approaching concept. That's where you'll get stuck. All right, let's try number 2. Number 2 says, as the limit as x goes to 2. Now, x goes to 2. This is x going to 2 from the left. This is x going to 2 from the right side. So as x goes to 2 from both sides, what is the height going to? That's really the kicker. What's the height approaching? So from the right side of 2, which is right here, 2 is right here. From the right side, I'm approaching a height of 2. From the left side, I'm approaching a height of 2. So if I rode that like a roller coaster, the heights go to approach a 2, and the heights on the left approach a 2. Now here's where the kicker is. Some people see the hole and they go, wait a minute, that's got a hole, so nothing is there. But that is where you have to be really clear what the concept is. Remember before I said you have to be within a box, you have to be within plus or minus epsilon, right? So even though this doesn't exist, that's where I'm going. That is where I'm going. It doesn't matter that it doesn't exist. I'm heading towards 2 from both sides. So again, it's like telling your friend, okay, let's meet at Charlie's restaurant, but when you both get there, Charlie's restaurant is missing, but you're both at the same destination, okay? So it's slightly tricky. Try to remember that a hole is not an NDE. Remember, we talked about the 3 cases of an NDE, and a hole is not one of them, right? Unbounded gap, increasing oscillations. Not a hole. This is the most tricky case. You might just want to like make a note to yourself here to remember this one for our first test and for the final. So a limit does indeed exist at a hole. These are not DNEs. Okay, let's try another one. And you can always stop the video and try to do it without me, and then we can come back and compare notes. So let's do this one. Limit as x approaches 5. So you're going to 5 from both sides on the x, and then what are the corresponding heights doing? Well, the height on this side is approaching a 1, and the height on this side is approaching a -1. So would we say the limit exists here? No, it doesn't exist. Very good. It's like I can hear you. What would we say the answer to this is? Very good. It's DNE because they are not approaching the same height. See, here they're approaching the same height. Here they're approaching the same height. Here these two are not going to the same destination. They're going to different destinations. So this is a DNE, and again, the reason being is because we have a gap. So they asked you here to explain why. So the reason why is because as x approaches, it approaches a different value from the left as from the right. I'm noticing this video is already 9 minutes. I think we can get the rest through. Okay, as x goes to pi over 2. So as x goes to pi over 2 from the left and the right, on the left side, what is the height doing? The height is going to positive infinity, coming in from the left. Coming in from the right, the height is going to negative infinity. Would these two people end up at the same place? No, they wouldn't. They wouldn't. This is a case where it's what? What is it doing? It's a DNE because it is unbounded. It's unbounded. Remember, if it's unbounded, if it's not going to a particular destination, it doesn't have a limit. Okay, so that was the case I showed you earlier. All right, now how about this one? Cosine of 1 over x as x goes to 0. When you see it colored in so distinctly like this, it means it's increasing in oscillations. Okay, so this is a case where you have sort of that target box. You're trying to catch the output, and it's jumping in and out of it. You can't catch it. It's jumping in and out of the target. So for this one, it's DNE because it's increasing in oscillations. Right? It never goes to a particular destination. It just keeps jumping in and out of what it's supposed to hit. Now notice this one is oscillating, but it's just oscillating at a standard rate. It's not increasing or decreasing. So the oscillations are not the problem. The problem is if it increases in its oscillations. So here we go. As x goes to 1, as x approaches 1 from both sides, what does the height do? On the left side, the height's going to 0. The height is physically around 0. And coming in from the right, the height is going to 0. So it's going to 0 from both sides. So the answer to this is 0. Okay, gang. So what I wanted you to learn from here, just a quick recap, was that limits can be done 3 different ways. Analytically, we'll get to that. Graphically, that's what we're working on now, and with a chart. So you can see here, as x goes to 2 from both sides, you can see that the output values are approaching a 3. We don't really do charts just because they're incredibly time consuming, but you can generate a chart to find a limit. And I talked about the 3 cases where the two-sided limit fails to exist. I talked about the formal definition of a limit. And then we worked through some examples. These, again, are very similar to what is on your homework. Now, in terms of handing in your homework, as you can see for limits, you're not really required to hand in any work. If it has a distinct answer, you just write it. If it doesn't have an answer, you can write DNE. You can you can explain why it's DNE. Okay? And then that's a wrap for what we're going to cover for 2.2. We are starting 2.3, so I'll pick up my next video with 2.3. That is part of this week's assignment. All right, catch you again soon. Bye-bye.